Okay, here we go with problem number 3, and this one is a doozy, so I hope I can do it justice. So it starts out easy enough, not too bad. We want to write w squared and w to the third, so this is really similar to the previous problem. One thing, though, is that this is written in a weird-looking form because all we have to do, though, is just abbreviate this. This is cis. So this is the same as 2 cis pi over 3. So if we want to do powers, I find it's easiest to write it in exponential form or Euler form. So I'm going to rewrite it again as 2e to the pi over 3i. I don't know. For me, I just like writing it in Euler form when then I can square it. So w squared is going to be, we square the modulus, and then we multiply the argument by 2, by the power. Okay, power of 2 multiplied by 2. So we get 4e to the 2 pi over 3i. Okay, and then w to the third, that's going to be 2 to the third, e to the 3 times pi over 3i. So that gets me 2 times 2 times 2 is 8, e to the pi I. So 3's cancel out. All right, so then they want me to sketch this on the Polygon diagram, and they want me to start with w to the 0. W to the 0, anything to the 0 is just equal to 1. So 1 would be right there, and then w would have a magnitude of 2 and a rotation of pi over 3. So pi over 3 is somewhere around here, so it would probably be around here. So here is my, let me scoot that up. Here is my w to the 0. Here's my w to the 1. And then the next one, w squared, is 4 pi to the 2/3. So 2/3 pi would be 1/3 pi, probably around here. And it's going to have a magnitude twice as big, so maybe around here. Okay, so that would be w squared. And then w to the third is going to have a magnitude of 8. So here's 8 and a rotation of pi. So I already did my rotation. My rotation of pi and a magnitude of 8. So it's going to be here. So here is my w to the third. Okay, so really similar to the previous problem. And now, though, they want us to form a quadrilateral. So for the next part, they want us to form a quadrilateral. So here's the next part. Where's that other paper? Here it is. So these 4 points form the vertices of quadrilateral Q, and we want to find the area. And they tell us what we should get, so that's nice. It's always nice to know where we're headed. Okay, so I am going to connect these. These are going to be my vertices. And here I go. So when I first did this problem, when I first worked through it, I actually figured out exactly where these points were by converting these to rectangular form, and then I graphed them really precisely. And you can do that really easily on your graphing calculator. You could change them to rectangular form, but I realized that I don't even need them in rectangular form. I don't need them precisely graphed because there's actually a really easy way to get the area of the shape by breaking it up into triangles. So I'm going to break it up into triangles from the origin. So here is my first triangle, okay, right here. There's my first triangle. My second triangle is right there. There's my second triangle and my third triangle. So I can highlight, let's go ahead and highlight these so we can see them clearly. See, I've got this nice little triangle here, and then I've got this nice little triangle over here. Well, let's see, we'll do that one and this one. All right, so how does that help me? Those are ugly little triangles, right? Well, it doesn't, we don't care if the triangles are right triangles or not, because we actually have a formula in our formula packet for non-right triangles. So I don't even care what kind of triangles these are because I have a formula, and now where did I put it? It's under the trig stuff. There it is. Area of a triangle, if it's not a right triangle, we can just do 1/2 a times b sine c. So if we know two sides of the triangle and the angle in between them, we can find the area. And sure enough, we have the two sides. We have this side and that side. Those are my magnitudes, and the angle in between them is pi over 3. So as we've noticed, when we raise an imaginary number to a power, the rotation is always the same, pi over 3, pi over 3, pi over 3. So I know all three of these angles here. I know all three of these angles. So over here, show that the area, I'm supposed to do it on this page, right? So if I call the blue one area 1, I have my formula, let me write down my formula again, 1/2 a times b sine c. Okay, so the sides of my triangle for area 1, I have, this is going to be 1, this is going to be 2, and the angle in between is pi over 3. So I'm going to have 1/2 times 1 times 2, because those are the magnitudes of those vectors, times sine of pi over 3. All right, and now if I use my unit circle, pi over 3 is that 60-degree angle. So this is 1/2, this is pi over 3 over 2. So sine of pi over 3, sine is root 3 over 2. So this is going to be, if I simplify this out, 1/2 of 2 is 1, 1 times 1 is 1. So 1 times square root of 3 over 2, which is just equal to square root of 3 over 2. Okay, I'm going to do that for the second triangle as well. It's going to be equal to 1/2. And then triangle 2, it goes like this, right? It has, this one has a magnitude of 2, this one has a magnitude of 4, and the angle in between here is, again, pi over 3. So 1/2 times 2 times 4 times sine of pi over 3, because that is the nature of when you take an imaginary number and raise it to a power, the rotation in between each one is the same. So it's pi over 3 again. Okay, so if I simplify this, I get 4 times, again, square root of 3 over 2. And I can reduce that. That gives me 2 root 3. Okay, and then area of triangle 3. I'm not going to draw the picture. It's on the other page. The other page right here. This is 4. This is 8. Okay, this side is 4. This side is 8. So it's going to be 1/2 4 times 8 times sine of pi over 3 again. Yay! It doesn't matter what exponent I take it to. It's always going to be the same right here. Pi over 3, pi over 3, pi over 3. Because remember, we were multiplying pi over 3 times the exponent. So these angles in here are all multiples of pi over 3. So when I break it up, each one of them is just a pi over 3. I'm just adding another pi over 3 each time I raise it another power. All right, so if I simplify that, I get 1/2 of 4 is 2. 2 times 8 is 16 times square root of 3 over 2, which is 8 square root of 3. So the total area is, I need to add these three together. Actually, to add them together, it's probably going to make more sense to add them all with a common denominator. So that's going to be root 3 over 2 plus 4 root 3 over 2 plus 16 root 3 over 2. And they already have a common denominator, which is 2. These are all like terms. Be careful. Remember, this is 1 square root of 3. So 1 plus 4 is 5. 5 plus 16 is 21 square roots of 3, which matches what we were trying to find. Okay, there are other ways to break up that shape to figure out the area and still get this. But this way, using this formula, 1/2 AB sine C, is the best way to set us up for the next problem. Okay, because here they're saying they want sort of a general form for this equation. If we chose any number for n, we could choose any number for n, And we are going to add together a whole bunch of triangles for whatever number of n I choose. Okay, so here's the weird part. The n on the exponent, it really doesn't matter what goes in here, what goes on the angle. They could have chosen to keep it as 3 or keep it as 4 or 5. It doesn't matter. You know, if we are finding the fourth term, you know, where we have 4 triangles, these are both going to be a 4, and it's not going to change anything when we do this. These numbers are just going to stay consistent. So, because notice when we were doing this, it was always a difference of pi over 3, pi over 3, pi over 3. So it really doesn't matter that they put the n here. It's kind of arbitrary. What it is going to affect, what the n is going to affect, are these numbers in front. It's going to affect the coefficients. So the sign of the angle it's always just going to stay whatever this is. Because when you raise a power of it, it's just going to be a multiple of this. So this is always just going to stay the same. It's always going to be a rotation by pi over the given number that you've chosen for n. So this part, you really don't have to worry about that. You don't have to worry about this. That just takes care of itself, because notice in my equation, it was always sine of pi over whatever we had chosen. So the fact that the n is changing doesn't really matter, because you're just going to find the sign of whatever that number is. But what we do have to pay attention to is the part in front, the coefficient. The coefficient is the interesting part, because what we have for our coefficient, we have this plus this plus this. How can we get it into this form? All right, so if I want to find the area of the polygon n, and it's going to be formed by taking z to many different exponents, right? So it's basically just adding these together n number of times. So we'd have to do these n number of times. So let's just write down what we have right now. Right now I have this plus this plus this, but notice they all have sine of the angle. And the angle is always going to be the same, because no matter what we start with and what exponent we go to, this is going to stay consistent, right? So the sine of pi over n is going to stay consistent. That's always going to be the same. But what did we add to it? We added this plus this plus this are going to get added together. Okay, so I can factor out the sine of pi over 3. Okay, so I'm going to, actually maybe I don't have much room. That's why I'm trying to avoid writing this all down. So if I add this plus this plus this, I can factor out my sine of pi over 3. So I'm going to have this number is 1, plus this number was 4, plus this number was 16, plus dot, dot, dot. What number would be to the nth term? That's what we got to figure out. And that's all going to be times sine of pi over n. Because every single one of these, even whatever term we're going up to, is going to be a sine over n. Okay, so I don't know what is going to, what we're going to be going to. So we can think about rewriting this in terms of n. So if I was just doing one term, I would only have 1. If it was just z to the first, I would just have that one. Sorry, wait a minute. That was, now I'm getting confused. That was z to the 1. Z to the 1 was this one. Z squared was this one. Z cubed was that one. Okay. So anyway, I'm going to be adding these together. And so if I'm going to be adding these together, I notice that this is a geometric sequence. This is a geometric sequence. I want to find the sum of this geometric sequence. How can I get the sum of a geometric sequence? Sum of a geometric sequence. And fortunately, there is a formula for this, sum of a geometric sequence. So I want to find a general form for this. And I don't even have to think that hard, because there is a formula in my formula packet. So I'm going to go to my formula packet, and I know I have the sum of a geometric sequence. Here it is. Find the sum of n terms of a finite geometric sequence. We're taking the finite geometric sequence because we're going to have a number n. We're going to know what the last term is. Okay, so, and here's our formula. So I'm going to copy this down. So the sum of a geometric sequence is the starting value times the common ratio. That means what are you multiplying by each time? Raised to the n, there's our n, minus 1, all divided by the common ratio, minus 1. Okay, oops, my phone is barking. Okay, so here we go. The starting value is 1. That's my first term. The common ratio, what am I multiplying by each time? I'm multiplying by 4. Each time this is going up by a multiple of 4. So 4 to the n, minus 1, all divided by the common ratio, which is 4, minus 1. And so we end up with 1 times 4 to the n, minus 1, over 3. And notice they want it in this form, like that. So I can separate that out. That would be 1/3 4 to the n minus 1. That is going to give me, and then I'll bring down my sign of pi over n is my answer. That was problem 3. So yeah, this part D, super tricky. Realizing that you have to figure out the sum of geometric sequence is like, what? But if you had just figured out how to factor out the sign part, I think that's, that's really positive move. All right.